going to share my screen. Yep. Sharing screen. And we stopped here, right? So if you guys remember from yesterday, we were talking about the cardiovascular system, okay? And we talked about kind of stroke volume and heart rate and some things as it relates to the heart. So we're now going to talk about blood, and then we're going to talk about blood vessels a little bit. And so if we look at what blood is made up of, okay, and I think I said yesterday that I feel like that blood is one of the most kind of appreciated pieces of everything in the cardiovascular system. A majority of your blood is water, okay? And so water in your blood is what we're going to kind of loosely refer to as plasma. Now, I say that plasma is about 90% or so water, okay? And it's got a few plasma proteins in there, and then it's got a few kind of other things that we're not really going to kind of talk about. But plasma usually makes up maybe somewhere between 50 and 60% of your blood. Okay, so you have water in your blood. That's why it looks and appears to be liquid. The other part of your blood is going to be red cells, white cells, and platelets. So it's these kind of more traditionally thought about blood blood cells. And they are referred to collectively as hematocrit. Okay, hematocrit. And hematocrit is almost exclusively red blood cells. Your red cells are about 99% of the cells that are going to be in your blood, and then less than 1% or thereabouts are going to be white cells and platelets. If your white cell count goes up appreciably, that's usually an indication that you have some kind of systemic sort of infection, or that potentially you have maybe like leukemia or something, or you've got cancer that is populating your bone marrow. So typically in a normal person, hematocrit is going to be somewhere around maybe 40 to 50%, kind of averaging out about 45% of your blood volume. Okay, we can, by manipulating several things, we can alter the percentage of your blood that is plasma and the percentage that is going to be hematocrit. And so I'll talk about that in just a couple of slides. Okay, so the key thing about the blood that is going to be really, really useful for us from an exercise standpoint, and in general, just from like the way that we tend to function standpoint, is some of the properties of the red blood cells. Okay, so your red blood cells are always in this state of flux. They have a half-life of maybe 90 to 120 days. And their primary function of the red cells is very singular. It is to transport oxygen, okay? And so we have, because of sort of the structure of red blood cells and their makeup, and then the amount of red blood cells that are in our blood, we have sort of evolved to a place where our blood is amazingly good at binding oxygen and allowing us to kind of move around and carry oxygen. So that allows us to provide a huge amount of energy for ourselves via aerobic metabolism. Okay? So the thing about red blood cells that allows them to bind a huge amount of oxygen is this thing called hemoglobin that is contained within all of them. And so hemoglobin is going to bind 4 molecules of oxygen. You have about 250 million hemoglobins per red blood cell. Okay? So a single red blood cell can bind about 1 billion molecules of oxygen. So it's this huge, huge amount. And you have several 100 million red blood cells in your body. Okay? And so you can imagine then, what we've got, like 10 to the, 9th or the 12th or some giant number of oxygen that can be bound up in your blood. That's what I want you to take away. You don't have to know these individual kind of numbers. I just want you to see them and hopefully impress upon you that this is a huge, huge, huge amount. Okay. So The thing that makes hemoglobin so good at binding oxygen is that it contains iron. Okay, it has these heme proteins in there, and they contain iron. Uh, Iron has a positive 2 charge, and so it's going to be very powerfully attracted to oxygen. And the oxygen is going to be held on there very, very well. Okay, and so having hemoglobin and having red blood cells in our blood allows us to bind about 70 times more oxygen and carry about 70 times more oxygen in the blood than we could ever hope to if we did not have sort of our red blood cell and hemoglobin set up in the way that it is. Okay, so having all of this is really, really advantageous for how we like to run metabolism in that way. Okay, so if we look at how O2 is transported in the blood, I want you to appreciate that about 98% of O2 is bound to hemoglobin. But there is a small amount that is bound that is just going to be dissolved in plasma. So you have some oxygen in your plasma, okay? It is not all bound to hemoglobin. This is going to be helpful when we come back and talk about kind of where we carry carbon dioxide in the blood, okay? The other cool thing about hemoglobin is that when we are at kind of not a particularly high altitude, so like we're in Oklahoma, you know, and we're like 200 feet above sea level or something here, that hemoglobin is, there's enough, hemoglobin is so sensitive. I'm trying to think about the best way to kind of characterize this. Hemoglobin is very strongly attracted to oxygen, okay? And there is enough oxygen in the air here, let's just say like at sea level, and it's going to go down a little bit as we go up to altitude, but at most altitudes where humans live, that our hemoglobin is going to be about 98% or more saturated under most sort of normal conditions, provided you have good normal pulmonary or lung function, okay? So if you've ever been to the doctor, and I should have brought mine from home, it was one of the first things we bought during COVID, because they thought that was one of the markers of when you need to go to the hospital. They put the little thing on your finger, right, and it tells you your pulse oxygen. It shines a near infrared light in, and it will tell you, put that little thing on there. And so if we put it on most of you guys here at rest, it's going to say you're 96 or 97 or 98% saturated in the hemoglobin. This is way more than what our body actually requires. When you take exercise phys with Dr. Mike, you guys will spend like a whole day talking about, there's something called the oxyhemoglobin dissociation curve. And so you're going to get into the biochemistry of sort of how much oxygen needs to be in the air and how that relates to the amount that's going to be bound to or saturating hemoglobin, and then what the tissue saturation, so like how much oxygen needs to be in a particular tissue in order to drive a certain amount of oxygen out of the blood off of the hemoglobin to go into that tissue. For our class, just know that there's lots of saturation on red blood cells. So there's high O2 content on red blood cells in your blood. When you get out to, say, muscle tissue, there's much, much lower O2 content. Okay, the mitochondria use up most of the oxygen. And so there's this big difference in partial pressures between the oxygen. So at muscle, oxygen wants to come off of the hemoglobin in your blood and go into your muscle so your mitochondria can use it. And they use it up, and it keeps the partial pressure of O2 in the muscles really, really low. In exercise phys, you guys probably did this already in physiology, but in exercise phys, y'all will talk a lot more about kind of the intricacies of that curve and why it's not a straight line, and how changes in pH and changes in temperature and things that occur during exercise are going to shift and move that particular curve around. There's some really interesting things that happen, but it's really kind of beyond the scope of our class. Okay, so I say all of this, and Emma, I see your question. I say all of this to make one kind of singular final point for you, okay? If anybody ever asks you, okay, and they say, is a lack of oxygen a limiting factor in your exercise performance under almost all conditions, okay? We go to Mount Everest, that's a whole different story, but at sea level, a lack of oxygen on hemoglobin, a a lack of oxygen being able to get into skeletal muscle it's very, very rarely the thing that limits your ability to continue doing some kind of like exercise. Okay. We're very good at bringing oxygen in. We're very good at getting it into our blood, and we're very good at getting it from the blood into our working muscles. Okay. Now we go to altitude, and it changes. There's less O2 and there's less air, and so the O2 partial pressure goes down. So we're going to get less saturation. Where it really becomes an issue is people that have pulmonary impairments. You have COPD, you have emphysema, you have cystic fibrosis, you have something where your lungs don't function correctly. Then that can limit the amount of oxygen that we can get in, okay, and then get in on the blood, and so your hemoglobin saturation will fall. A lot of the people that had COVID and had pneumonia and some of those things, their O2 sats were falling because their pulmonary function was not correct. And that can be really dangerous, and that can absolutely limit exercise performance. But if you guys all go run today, unless anybody's in Denver or someplace higher than Denver, like all of that, then it's probably not a lack of oxygen that's going to make you stop or make it feel difficult for you. Okay, Emma, your question.
Yeah. Oh my goodness. Okay. I have two questions, both of which are probably not like super relevant to the class, but I am kind of curious. So those like pulse ox thingy majors that you put on your finger with this infrared light, how does that actually like tell how much oxygen is in your blood? Like what? You
want me to explain the absorption and refraction physics of near infrared light? Is that what how that works? It's pretty simple. So we shine. So it shines a thing, the wavelength, it's a near infrared light. That's the wavelength. Yep, there we go. So Julia's got one, okay? Shines this kind of reddish looking light in. And it shines it in at 2 wavelengths, which I am forgetting. I swear, like, I could look it up. But one's like 680 and the other one is something else. But the point is that those wavelengths, one of them is absorbed and the other one is reflected by hemoglobin that has no oxygen, and then the other one of them is absorbed by hemoglobin that has no oxygen, and the other one is like reflected by hemoglobin that has oxygen. It's one of those. It does it differently at each wavelength, and so what it does is we know how much of each wavelength we're shooting in there, and then we collect how much of each wavelength gets bounced back to us. And from all of that, it's just a ratio. We do some calculations, and it tells us what those things are. We have a much more sophisticated device in a couple of our labs downstairs here that does the same thing. And we can have people do like all out exercise, and you can watch the oxygen levels in capillaries sort of begin to fall as you exercise. And if you're pushing people towards fatigue, they start extracting more and more and more oxygen into the muscle. And so where it's measuring that microvascular circulation in the capillaries and stuff, then deoxyhemoglobin begins to go up. And then as it's going to kind of come down, you can predict when fatigue will occur at kind of certain levels. And usually it'll dip a little bit, and then if you can sustain exercise, it dips and then it kind of levels off because you can properly match things. That's kind of how it works. It's actually a pretty simple, the physics of it's pretty simple. The electronics of building the thing that shines the light and then the thing that collects it back is more tricky.
Makes sense. Yeah, my aunt had COPD, and she when she would get like a lung infection, which was like literally all the time, her pulse ox would sink to like 76 sometimes. It was scary.
That is terrifying. It's absolutely terrifying. So really, if you get stuff like out of the 90s, then you probably need to like go to the doctor or call it in. But I mean, if you're in the 70s, like that's real bad.
Yeah, and it didn't help that like we are from Denver, and so we were at altitude, and then she can't breathe.
Oh yeah, no, that's also sort of a double whammy.
Yeah, bad combo. My other like quick question, which I don't know if this even has an answer, but like, does the fact that we carry like way more oxygen in our blood than we actually need to, does that contribute at all to like, sort of like, I don't know, reactive oxygen species and stuff like damaging our cells and whatnot, just because we have too much oxygen getting carried around, or because it's in its diatomic form, it's not problematic?
No, it's not. That part is not problematic. The reactive oxygen
Okay.
species is a separate. That's a separate issue.
Okay.
Very much in some ways related to like systemic inflammation and having too much LDL and eating too much saturated fat and there's some other things that are going to contribute to the formation of the reactive oxygen species. And it's not that we have too much O2 in that particular way. So that's a good question. That's a good question. Okay, so we've talked about oxygen and how we get oxygen into the blood, and that's kind of the big deal. I guess before we go on and we talk about CO2, I do want to mention really quickly that you can manipulate very, very easily the amount of red blood cell, the ratio of red blood cells to plasma in your blood. And it's pretty simple. Anybody you guys have been here in Oklahoma, or you've been someplace where it's hot and you've been doing stuff outside for about 10 days or something, and you become acclimatized to it being very, very hot. The way you become acclimatized is you sweat, and then it drives things at the kidneys. And what you do is you increase the amount of plasma in your blood, so you've got more plasma to sweat off, basically. And what happens when you expand your blood volume, where plasma goes up, then the percentage of your blood that is red blood cells is going to go down. So when we do heat acclimatization, that tends to sort of drop down a little bit your hematocrit percentage. If you want to make your hematocrit percentage go up, you need to go to altitude. And so go to Denver or go someplace higher than all of that. Go to Mount Everest Base Camp or something. And the lack of O2 there does two things. One, it stimulates your kidneys to make erythropoietin, which is a hormone that drives the synthesis of red blood cells. But when you go to altitude, the other way to try to compensate for things, and Emma, I don't know if you experience this when you go back and forth potentially, is when you first go to altitude, you end up dehydrating yourself. Your body naturally dehydrates itself. And when you filter, you filter your blood at your kidneys. When you make urine, what it's doing is it's filtering and it's taking plasma basically out of your blood. And so when you first go to altitude, one of the natural responses is that you're going to start making disproportionately more urine. And so you're going to pee off some of the plasma in your blood. And so it leads to what we call hemoconcentration, where red blood cell as a percentage of total blood volume is going to go up. That's going to actually increase in some ways what we would call the oxygen carrying capacity. You can carry more oxygen per unit of blood. But the problem is you actually now have less blood, which is in the bigger picture a bad thing. And that's why that in combination with less air and less hemoglobin saturation is why it's hard to exercise at altitude. And so people that want to do this, if you want to be a better, having more red blood cells and having a greater blood volume is really good for endurance exercise performance. So if you're Lance Armstrong, you just cheat and you take artificial erythropoietin and it makes you have more red blood cells. Your blood volume goes up and you have more red blood cells. Similarly, we could send all of you guys down to the CSL plasma place and you guys could donate some plasma and donate a pint of red cells as well when you go and you give blood. And then we could wait about 2 months, let your blood volume go back. We could spin those down and infuse you back with your own red blood cells, and you would immediately be a better distance athlete, like way better. Like knock 30 seconds off your mile time, kind of better, just by having an expanded kind of red cell volume. But we could get on, maybe not on Amazon, but we could Google and we could buy some erythropoietin like right now online if a person was interested. But the other way to do it, quote unquote, legally is that you'll go and you live at altitude, but then you live like in Denver, but then you got to drive down every day off the mountain, basically out to the farmland in eastern Colorado to go run. or to go do your cycling exercise. And so you exercise at and you train at sea level because you can work harder because there's more air. And then you go back, but you live at altitude. And so it drives you kind of get the double whammy effect of both. They make altitude tents. You can buy a tent that you sleep in at night, and it just has lower O2 content. And that kind of helps drive red cell synthesis in those ways. Doing it that way, though, you can only get it to go up so much. The Olympic athletes and things, you'll probably hear about this summer. If you're a distance athlete and you're a professional, you have what's called a physiological passport. And you have like 6 hours or something, whenever they ask you to, wherever you are, you have to report to a lab and they'll draw blood and they'll look at your red cell count, they'll look at your hematocrit percentage. And we think that from going to altitude, like naturally people can get to maybe 51 or 52% of their blood can be red cells. Anything really over that and you're taking erythropoietin. To be honest, though, you get over 50% and your blood becomes really sludgy. And when you sleep at night and your blood pressure drops and your blood moves really slowly, you get a lot of blood clots. And so there can be a lot of dangers if you take too much EPO as well. So there's a lot of fascinating cautionary tales of especially cyclists that do those things. So if you guys have Dr. Larson, Rebecca she still is, she was a sort of world professional level cyclist, and she was on several professional teams, and she can tell you some stories. So anyway, the other thing that we carry in our blood that is going to be important for exercise is carbon dioxide. So you use all this oxygen in your mitochondria and you make ATP, but one of those byproducts of what you make is carbon dioxide. And so you have to get the carbon dioxide out of your muscles into venous blood, basically, to get it back to the lungs so you can get rid of it out into the atmosphere. And so we carry carbon dioxide in our blood in 3 ways, okay? You have some, just like oxygen, that is dissolved in the plasma. That's maybe 10%, okay? And that's going to determine what we call the PO2, or the partial pressure of CO2 in your blood. This always kind of blows my mind because I was never taught this until I was a graduate student, but we also have carbon dioxide that binds to hemoglobin. It basically trades places with some of the oxygen. It's called carbaminohemoglobin, and that's maybe 1/5 to 1/3 of the CO2 that's going to be carried, especially in venous blood. And then the last bit, which is the majority, is going to, when you put CO2 and you dissolve it in the water that's in the plasma, it forms something called carbonic acid. And then when you have an acid that occurs in water, that acid wants to dissociate. And it dissociates into a hydrogen ion and then something called HCO-, which is bicarbonate. You guys may have heard of bicarbonate if you've ever had an upset stomach or you've ever had acid reflux and you've eaten Tums or Rolaids or taken Mylanta or something like that. Bicarbonate is a base and it functions as a buffer. And so you increase and you drink something or eat something that has bicarbonate in it, and it wants to essentially neutralize stomach acid. Well, you have bicarbonate in your blood, and that bicarbonate then is going to, when it gets back to your lungs, it's going to bind back to these hydrogen ions, and then this reaction goes in reverse and you get some CO2 that you then kind of breathe off. So we use these bicarbonate ions to help us exercise at a higher level. The bicarbonate buffering of things and how that functions in conjunction with your lungs is something you'll spend a lot of time talking about in exercise phys. Again, it's kind of beyond the scope of this class, but I just want you to know that we are really good at binding oxygen and carrying it, and then we have these different ways that we're going to get this CO2, and then we're going to breathe that CO2 off. We're going to talk about the process of how we do that in the next few slides. Okay, so gas exchange at the tissue level. What I want you guys to take away from all of this, and again, there's a reason, and you guys probably hate us for doing this, but there's a reason that we make you guys take chemistry and that we make you guys take kind of intro to biology and all of those things, because There's some concepts that are involved in all of that that are really critical for normal physiological function, and then for the stressors that exercise place on physiological function. And so when we talk about gas exchange in tissues, what I'm showing you guys here is, here's a capillary, and here's a single red blood cell in the capillary. And then on the left, we have what the cartoon is calling respiring tissue, but just assume that this is skeletal muscle, okay? This is skeletal muscle here on the left. This is a capillary that is running right next to that skeletal muscle fiber, okay? So if blood moves based upon differences in pressure gradients, gases, so in this instance, carbon dioxide and oxygen, are also going to move based upon differences in, we're going to call them partial pressure gradients, but they're really gradients that are related to the concentration of those gases from sort of one place to another, okay? And so if we imagine this scenario where I have this, billion molecules of oxygen that are bound to my red blood cell here, that exerts something that's called an O2 partial pressure sort of in the capillary. Inside my respiring or inside my skeletal muscle, I have a much smaller amount of oxygen that's going to be sort of floating around inside that skeletal muscle fiber. So I have a very high O2 partial pressure here in the capillary because of all of this on my erythrocytes. I have a very low one in muscle tissue, and so the partial pressure gradient is very big. And what happens is that oxygen comes off of the hemoglobin here, and it wants to diffuse into skeletal muscle, okay? It gets then used in the skeletal muscle, which keeps the partial pressure very low. As this happens, I use oxygen, I make carbon dioxide. So I have relatively more CO2 inside this muscle fiber than there is right here in the capillary. So that drives things in the opposite direction. So CO2 wants to diffuse down its partial pressure gradient from inside skeletal muscle into the capillary and either get dissolved in the plasma or to bind onto the hemoglobin here or to become bicarbonate, okay? When these things, you guys will see, when these things get to the lungs, the entire thing happens in reverse. The CO2 leaves the blood and goes into the air in the lungs, and then the oxygen comes from the air in the lungs back into the capillary, okay? But this is how gas exchange occurs. It's all based upon differences in concentrations of these gases. And the really cool and interesting thing about this is that we have evolved this way to where we have very high concentrations of oxygen in capillaries, which drives a bunch of it into the tissues that need it. And we have then necessarily lower levels of carbon dioxide so that we can pull the CO2 out of the tissues that are making it and then be able to get rid of it, okay? Does that make sense, right? We're not gonna do any problems of all of this. We're not gonna get into all the intricacies of partial pressures and how we would calculate the actual driving pressure of oxygen based upon atmospheric pressure and all of those kinds of things. But I just want you to get the big picture of this, okay? Just the big picture. Julia, you had a question.
Yeah, I was just gonna make sure that that's also what happens when you're resting, not just exercise. Like when you're asleep, that's what, and you're not doing anything.
Yeah,
okay.
No matter what happens is that you basically only bring in enough oxygen into the tissues to kind of satisfy what you need. As you're not using as much when you're resting, then the sort of partial pressure in skeletal muscle that is not respiring very much is going to go up a little bit, and it's going to even those things out just a little, and so you're going to have less wanting to try to come in. And because you're making less CO2, then there's less, you're still going to be really good at getting the CO2 that's going to come out. But yeah, this occurs no matter what's happening, but it becomes even more pronounced during exercise because you lower the partial pressure of oxygen inside skeletal muscle to an even greater extent during exercise because you're using more oxygen and you raise the partial pressure of CO2 in the muscle during exercise because you're making so much more CO2. And so it actually enhances the ability then to drive CO2 out and bring more oxygen in. Okay. Questions about that? Anybody? All right, let's talk about the vascular system. We have arteries, and then there's smaller kind of things that are called arterioles here that are going to take blood away from the heart. They're then going to branch all the way down and become capillaries. Capillaries are very small. They're so small in many instances that we got a single red blood cell inside of them, and that's all that can fit. You have these very extensive capillary networks that are going to surround pretty much every tissue that needs oxygen. And then the capillaries are going to kind of all work themselves back together and form these small vessels called venules. And then the venules are going to all eventually come together and make these larger ones that are going to be called veins. And they're going to bring blood back to the heart. Okay. So things to know. A lot of the action in response to exercise and other things is arteries are important, but it's really the arterioles that are going to be the place where a lot of changes and stuff are going to take place. We call arteries and arterioles resistance vessels. Anybody had physics 2? They have to talk about fluid mechanics or electricity and how electricity moves. But the idea of resistance is sort of a strange calculation, a strange parameter. And what it means is how difficult is it to move a fluid through this particular tube. And so we use arteries and arterioles. I don't know what I just did. No, go back. Okay, sorry. We use them and we can change their diameters. And by changing their diameters to some extent, we can make it easier or more difficult for blood to pass through them. And so that can alter blood pressure, and it can alter which tissues are going to get blood, which we'll talk about in just a second, okay? So the way that arterioles and arteries can change their diameters is they have smooth muscle, which is what you can see here kind of in the pink, that are going to surround those vessels. And in some conditions, we can tell that smooth muscle to contract, and it squeezes down those arteries and makes them smaller. In other instances, that smooth muscle will relax and the arteries will get bigger, okay? And so that's going to help us kind of direct blood flow into certain tissues, okay? This is like an electron micrograph all the way down to the very, very smallest level here. But this is, they've put dye into the blood vessels. And so you can see these kind of larger arterioles, and then you can note how, like, here's an arteriole, and then it branches right in this kind of perpendicular manner. And then you'll have these then third order arterioles. You've got a primary, a secondary, third order, fourth order, and they just kind of branch in these continuing perpendicular branches until we get all the way down out here to these capillaries that are going to encircle skeletal muscle or your small intestine or any kind of other tissue, cardiac muscle, and those kinds of things. Okay. So some really cool kind of pictures of all of this. I love this picture, mostly because it reminds me of the Michelin Tire Man. But what you see here is an arteriole, and you see these little rings that are going around the arteriole that look like a little baby and a little baby chub, or look like the Michelin Tire Man. That's vascular smooth muscle. And so that's what you see here. These rings are the muscle around the arteriole. And then what you see in this next picture, they have taken and they have dissolved the smooth muscle, and they've stained specifically for the sympathetic nerves that are going to connect to, or that are going to be embedded in the smooth muscle. And so what happens is we can give input and tell the smooth muscle to contract or not from the sympathetic nervous system. And so based upon input from epinephrine and norepinephrine, it will basically tell the smooth muscle to contract and squeeze things down. And I'll kind of explain how and why that becomes important in a couple of slides from now. Okay, so we can do all of that. We've pretty much already talked about capillaries to the extent that I want us to. So the next kind of big concept that we need to understand is the idea of what we call blood distribution, okay? So you have a certain amount of blood. That blood is in these vessels. Those vessels are going to take it, right? The arteries and the arterioles are going to take it to a particular tissue so that stuff can move around and get into and out of that tissue in the capillaries, and then the veins bring it back to the heart. Well, as you guys are sitting there right now, you have a certain amount of blood in your body, and a certain percentage of that blood is going to very predictable places, okay? And then when we change what it is that we ask you to do, like if I ask, let's say, Sunny to stand up and start doing jumping jacks or running in place, I can make her blood distribution change, okay? Or if I picked somebody, this is where it's always fun to be in class. Like I could pick someone. So John, are you a very good singer? John's not a singer. Awesome. Perfect. That's just exactly what I want to hear. If I ask John to start singing for us, like John, like what's your favorite song? Start singing your favorite song for us. You don't have to, okay? But usually in class, I'll have someone like stand up on their desk, and we'll go like all Dead Poets Society and be like, oh, Captain, my captain, kind of things from all of that. But if you did that, and let's just say people become nervous and they become maybe slightly kind of embarrassed that people are looking at them and their face becomes flushed, right? That's a change in blood distribution. I have evoked a sympathetic nervous system, a stress response, and I've changed where your blood is going. When you exercise, the same thing happens. These are these very predictable changes, okay? And so at rest, under normal conditions, so with most of what you guys are doing right now, blood tends to go to the most metabolically active tissues at that particular moment. And when people are resting, about 50% of the blood in your body is going to the liver and to the kidney. So we're cleaning the blood and filtering it at the liver, and we are making urine and filtering things at the kidneys. Those are the two most metabolically active tissues, okay? You may have some if you've just had breakfast or something. You will have some that's going to your stomach or to your small intestine. At rest, we only have maybe 10, 12, 15% that's going to skeletal muscle. Your brain's always getting a constant amount. Your heart is always getting a constant amount of blood. Not a lot that goes to muscles. When you start exercising, though, I can flip all of this around. If I have you do very intense exercise, I can send about 80% of the blood in your body, basically everything that's not going to your heart and your brain, I can send pretty much all of it to the skeletal muscle that is actively contracting during a bout of exercise. So it stops going to your liver, it stops going to your kidneys, it stops going to your stomach, it stops going to your small intestine or your large intestine, and therefore it can go to your muscles. Part of this, we think, is an evolutionary thing that is related to what's called a fight or flight response, okay? And so a fight or flight response is a very typical sympathetic nervous system thing. Imagine a scenario whereby my wife was showing me pictures from some people hiking in Yellowstone yesterday, and they encountered 3 grizzly bears. I don't know about you guys, but if I was within, say, 50 yards of 3 grizzly bears, I would need a clean pair of shorts. They are awesome, and I love them, but I want to see them behind the bulletproof glass of a zoo, right? But if you are about to encounter in the wild a grizzly bear or a mountain lion or a really mean squirrel or something, right? Or I don't know, another person who wants to, inflict harm upon you, it's probably best to send all of the blood to your muscles so that you can either fight them, right, or you can run away. Doesn't matter if I'm doesn't mean no good to be digesting food while I'm about to get eaten, right, in those ways. And so that's part of the sympathetic nervous system response. This fight or flight response is going to send all of it to our muscles and away from these other tissues. And so that's why during exercise, as you start contracting muscles, we can shunt all of the blood over there, okay? When you get hot, we're going to have heat stress. You're going to move blood to your skin. One of the reasons that exercise can be really, really dangerous when it's hot outside is that we lose most of our heat loss through sweat evaporation on our skin. And unfortunately, if you are well motivated, muscle's more important than skin. And if you are really, really motivated to exercise, you can actually begin to send blood that was going to your skin when it's hot to your muscles. And so then it's going to enhance the amount of heat stress that you're going to experience. So that can be a real problem in the midst of that. The system is set up that if people are really motivated, you can send a bunch. Your muscles tend to always win if they want more blood flow. Okay. So how do we get the blood to those places? This is just a cartoon that's gonna show kind of where it's going, either during heavy exercise or when you're resting. But how do we get the blood where it wants to go? And it's by this. It's by basically changing the diameter of arteries and mostly arterioles. And when we want blood to go to a particular tissue, then we send a signal to relax this smooth muscle. You relax the smooth muscle and the arteriole will get bigger. That makes it easier for blood to flow through there. It lowers the pressure inside, and that's going to make more blood want to go through. When I want blood to not go to a particular tissue, I send a signal through the sympathetic nervous system, and I contract and I squish down the smooth muscle. It squishes the arteriole. It makes it very, very small. The pressure inside of it is very, very high. Therefore, it's much more difficult for blood to get through. So what happens when I exercise, I relax the arterioles that connect to muscle, and I constrict the arterioles that are going to pretty much every place else that's not the brain and the heart. Okay. Again, it's a relatively elegant and redundant but quite complicated system of signals that lets us do all of this that are kind of well beyond the scope of this particular class. If this kind of stuff interests you, I'd be happy to chat with you a little bit later on. Some of my master's degree, we spent some time studying kind of the things that go into some of this signaling in that way. Okay. Okay. Let me talk about one more thing, and then we'll take a little break, and then we'll hit the respiratory or the pulmonary system. So, a final parameter where we're going to put everything together, okay, that I want you guys to know is something called arterial venous oxygen difference. I often refer to it as AVO2 diff or AVO2 difference. And so what the AVO2 difference tells us, okay, is pretty simple, but the way we arrive at the calculation is going to be a little more complicated. What AVO2 difference tells us is the amount of oxygen that is being taken out of arterial blood at the capillaries and then being used in skeletal muscle or cardiac muscle or in brain and nervous tissue in your brain or in your small intestine. Like, just pick, you can get an AVO2 difference across any tissue, okay? But it's really a measure of what we would call oxygen extraction. It's how much comes out of arterial blood and goes into a particular tissue to get used. We calculate it by, if we know the amount of oxygen in arterial blood, and then we know going into a tissue, and then we know how much oxygen is left in the venous blood that's leaving that tissue. If we subtract those two things from each other, then the difference is very clearly the amount of oxygen that left arterial blood to go into that particular tissue. Okay? This is really, really important. If we know AVO2 difference and we know cardiac output, we can calculate oxygen use, and in that way, energy expenditure in a given tissue, at least aerobic energy expenditure in a given tissue. In a practical sense, it's nearly impossible for us to actually calculate AVO2 difference. To do this, I would have to run a catheter. Let's just say if I want to know what the AVO2 difference is in your quad muscles, I have to run a catheter into your femoral artery and into your femoral vein. We need a cardiologist, or at least a well-trained cardiology nurse to run especially the arterial catheter, so that we can directly measure how much oxygen is in the arterial blood, and then we can directly measure how much oxygen is in the venous blood that's left in particular tissue. Okay, so, and one of the things that we do know that happens because of all of this, though, is that arterial O2 content tends to stay pretty constant, no matter what you're doing. As long as you're kind of at altitude and you're not at altitude and you have good pulmonary function, this side of things stays the same. You saturate your hemoglobin, there's X amount of O2 in there, that one stays the same. All of the changes that are going to be derived from changes in tissue metabolism are going to make this venous side fall even farther. And so, like during exercise, the venous AVO2 difference may go up 2 or 3 times, and all of that O2, the arterial side stays the same, the venous side just falls farther and farther as we extract more oxygen. Okay. I will show you guys, I think it's later on today, something called the Fick equation. And the Fick equation is going to let us calculate oxygen consumption, or essentially metabolic rate, at a tissue if we know cardiac output and we know AVO2 difference. Okay? So that's kind of that particular concept. Okay, so I'm going to stop sharing. We're recording, I'm sharing screen, and we're back at this, I think. Okay. Yeah, here we go. This is the start. So, in a weird kind of twist of things, we're going to talk about the respiratory system or the pulmonary system really quickly. Hit a couple of things, and then we're going to shift back to, in some ways, what happens during a bout of exercise to our cardiovascular parameters that we've talked about. And we're going to talk about the kind of things that happen in the pulmonary system in response to a bout of exercise. Okay, that's kind of how we're going to finish up today. So when I say the respiratory or the pulmonary systems, what I really mean are lungs, okay? And then the specialized structures in the lungs called alveoli, which I'm sure that you guys are intimately familiar with from anatomy and physiology. And then what we call pulmonary capillaries, which are the blood vessels that are going to surround all of those alveoli. Okay, so we're really kind of getting into the nitty gritty of the kind of cellular level structures that are going to be there in the lungs. Okay, we're not going to talk very much about the bronchioles or the branches of the bronchioles or the conducting zone versus the respiratory zone or any of those kinds of things. We're not going to talk about any of the anatomy kind of up here, right, in your nose or in your throat or anything else. We're really just going to focus for the most part on where is gas exchange occurring and kind of what is the big picture of breathing doing as we move through things, okay? So normally what I do right now is I have everybody sit up really straight and I have you take a big deep breath. You breathe in and then you let it go, and you breathe in and then you let it go, and we can feel our diaphragm kind of moving up and down, okay? So at rest, our mechanisms of breathing are mostly driven by simply the diaphragm, okay? When you're going to breathe in, okay, then the diaphragm is going to, right, contract, and it's going to drop, right? It's going to contract and it drops down. As you can see here, that expands this lung cavity. So the pressure inside the lung cavity drops because it gets bigger. And then when you open your mouth or your nose, then air is going to want to move in from outside, and it's going to want to come down and go into your lungs. Then when you want to expire, what you do is you relax the diaphragm. It moves back up to its relaxed position. That squishes down and closes down that space inside the chest cavity, which raises the pressure in there. And that increase in pressure then drives air out of the lungs, and you open your mouth or your nose and you blow that air off out into the environment, okay? So again, in this way, we have air, which is a combination of gases that are moving based upon sort of the air pressure gradients that we can create by moving our diaphragm up and down. During exercise or during kind of forced breathing exercises, we can bring in our intercostal muscles, and we can even make inspiration even greater or expiration even greater by sort of forcibly making the pressure go up more, by forcibly making the pressure go down even more. Okay, so pretty kind of simple, straightforward type of thing. The process of breathing, okay, the process of breathing, we're going to characterize this as a variable that we're going to call ventilation, okay, or VE. Okay, that's what it's going to stand for, ventilation. This is the amount of air that flows through the lungs each minute, okay? Ventilation is the pulmonary analog to cardiac output. If cardiac output is the amount of blood pumped by the left ventricle every minute, ventilation is the total amount of air that moves through the lungs over the course of each minute. Just like cardiac output, ventilation is the product of what we call respiratory rate, or RR, okay, which is in breaths per minute, and then something that we are going to call tidal volume, or in this instance it's just called the volume here, but tidal volume is the amount of air that moves into or out of the lungs with each inspiration or expiration. So if I know how many times I take a breath, and I know how much air I move for each breath, right? If I multiply the number of breaths per minute by the volume of air that moves per breath, I get this parameter that's called ventilation, or VE. And just like cardiac output, its primary units are liters of air per minute. So it's a liters per minute variable, just like cardiac output is a liters per minute. Now, if you take testing and prescription class, you guys will learn all about these other parameters here. What you see in the graph is, this is from a pulmonary spirometry test. And so there are some other things that we can measure. So what you note here, this little change right here, this is sort of normal, relaxed breathing. And so this change, right, this is your lung volume and how much air is going to be kind of moving. This is tidal volume. So this is your normal kind of breathing. But you have what's called an inspiratory reserve volume, whereby you could, if you need to, you can suck in way more air than you normally do at rest. You have some volume of extra that you can ventilate with. We have a kind of expiratory residual volume, where I can blow off or exhale more air than I normally do. And so we can kind of calculate what all of these things look like and arrive at some parameters, things like what we call vital capacity and functional residual capacity, total lung capacity. There's some variables we can calculate from doing this test. We're not going to use any of these things in our class, mostly because we don't talk about pulmonary kind of chronic diseases. We don't really talk about COPD or emphysema or anything else. Because it's kind of beyond the scope. It's not something that being more active can really help. So we don't really talk about it in class, but that's why we would do all of this, okay? And so if you're interested in prescribing exercise, especially to older adults, it's useful to know and understand these things, because you see a lot more people that have pulmonary disorders, and you need to change your exercise prescription, ask them to do things a little bit differently, because maybe they've got a reduced inspiratory reserve volume or a reduced expiratory reserve volume. That's going to have some kind of knock-on consequences on things, okay? Additionally, if anybody has asthma and you've ever had to go to the doctor, go to a pulmonologist to get tested for asthma, I can remember a really terrible experience of that when I was in high school, and you had to do a bunch of spirometry tests for those things. This is the stuff that they were trying to measure, okay? All I want you guys to know, though, is sort of what ventilation is, and it's the product of respiratory rate and tidal volume, okay? Okay, so how do we control breathing, right? How do we control breathing? You guys want me to do we want to do a fun exercise? Let me look at this. Shakota, are you there?
Yes, I'm here.
Okay, Shakota, how long do you think you can hold your breath?
Probably not very long.
Well, like, what's not very long? If we put a timer on you right now, you think you could hold your breath for 20 seconds?
Maybe 20 seconds.
Maybe 20 seconds? Class, should we see if Shakota can hold her breath for 20 seconds? Make her turn her camera on and do all of that? No, we won't. Okay. So The reason that I ask is, some of you can hold your breath longer than others. This is a fun thing when you have a toddler and they want to throw a tantrum and they want to, like, I'm going to hold my breath. Like, at some point you'll breathe again, right? Like, we cannot hold our breath and kill ourselves simply by holding our own breath, right? Do you guys know the reason why that's the case? Do you guys know why when you hold your breath, you build up this sudden urge to breathe, and at some point that urge becomes so strong that you will in fact breathe no matter what it is that you want to do? Do you guys know why that's the case?
Receptors?
Receptors. Very good, Nia. Yes, we do have receptors. We'll talk about what those receptors are recepting. We'll talk about where they're located, okay? So how many of you normally think about breathing? Like Chandler, you're sitting there right now. Have you thought about how often you're breathing once during class until I just asked you?
No, not really.
Not really, right? We never think about breathing unless we've done something and we're having to, like, kind of recover and we're like, oh, I'm breathing harder than I normally do, right? You don't ever think about breathing. It's kind of like your heart rate. If you had to think about breathing and making your heart beat, like, we'd all be dead, okay? Because we'd get distracted and forget about it, okay? You have areas in your brain, much like the SA node, that are going to send signals to your diaphragm to contract and relax, okay? So there are motor neurons that innervate the respiratory muscles. Those motor neurons are going to receive things from a place called the respiratory centers, which are in your brain. I believe they're in the thalamus, if I'm not mistaken. I probably should have looked that up before class today. I thought I had that straight. But there's a place in the brain, and it sends a signal. So even though Jessica's writing stuff and she's trying to, listen, she's going to remember to breathe because the respiratory centers are just going to fire and say, breathe, okay? The respiratory centers can be counteracted by you forcibly deciding not to let your diaphragm contract. But that only lasts for so long. At some point, right, you can't hold your breath so that you can kill yourself. They will fire, you will breathe, okay? One of the reasons that that happens is that the signal coming from them is going to get stronger and stronger as we build up things like carbon dioxide and hydrogen ions from metabolism that are going to make us want to breathe. So we need to, in an ideal world, we want to match how much we breathe so that our ventilation is going to bring in a certain amount of oxygen that is going to match the amount of oxygen that's being used by whatever tissues are undergoing metabolism. So at rest, when you're not contracting your muscles very much, we need to bring in enough oxygen so that our brain can function and our heart can continue to beat and we can continue to breathe, basically. When you start exercising, you're going to have enough for all of those tissues plus for whatever skeletal muscle you're going to have. And so we need a way to signal, hey, breathe more deeply, breathe more frequently, so we can increase our ventilation and do all of this, okay? And the primary way that this is done is by changes in carbon dioxide and oxygen. These two molecules are going to bind to receptors that we call chemoreceptors. And so you have these specialized cells that are going to detect increases in CO2 for the most part, okay? And a little bit of an increase in hydrogen ions. So when plasma, when blood becomes a little bit more acidic, which is an indication that you're doing anaerobic metabolism, that aerobic can't keep up, then it's going to tell the respiratory centers to make the diaphragm contract more deeply and more frequently, okay? So most of your chemoreceptors, especially the CO2-derived chemoreceptors, are located in the aortic arch and in your carotid arteries. So when we see increases in carbon dioxide concentration in those places, that drives an increase in your breathing, okay? And so what happens when you hold your breath is that you hold your breath, you're not blowing off any CO2. So the CO2 concentration in your blood goes up and up and up and up, and it stimulates those chemoreceptors in the aortic arch and in your carotid arteries, and those are then going to start sending stronger and stronger signals to your respiratory center saying, hey, we've got a lot of extra CO2 here, we probably don't have enough oxygen, we need to breathe, and we need to breathe right now to fix this. And eventually, that signal becomes strong enough that you cannot voluntarily not contract your diaphragm. You will contract your diaphragm, okay? And this is in some ways why people drown and those things, is that you can hold your breath for a certain period of time, but at some point your brain is going to make you breathe. And it's because of this buildup of CO2, okay? We also have stretch receptors located in the bronchioles. They're going to sense the stretching of the lungs, and that's also going to send some feedback to the respiratory centers to make you breathe a little bit more frequently, a little bit more deeply. And we do also have a level of conscious control. Like if I told Wyatt to hyperventilate, so I told Wyatt to breathe really deeply and take 6 really deep breaths and to go really fast, almost like you see on TV. And my wife, we never did this. They used to have a thing called Lamaze class. We'd breathe through the pain when you're going to have a kid, during birth. My wife was like, I don't care. I want the drugs. Just give me the drugs. In the midst of all of this. And then she got the drugs. And then, of course, they had to do a C-section. So it didn't matter because Ellis was being squirrely and squeezing the umbilical cord under her arm and shutting off blood flow. But if you do all of that, you can go, you can voluntarily change your breathing patterns to a point, okay? But really, okay, the primary controller of how often you breathe and how frequently you breathe, how deeply you breathe, so the primary controller of ventilation is carbon dioxide. Please write this down. It is important, okay? Probably be a test question about that, all right? Most changes in breathing are driven by CO2, which I've always thought is a little strange, right? You would maybe logically think that breathing is controlled by oxygen levels. And that you would think that, oh, my O2 levels are low, I need to breathe more. And it's actually not that. It's the thing that the oxygen is being made into in your tissues. When that goes up, then that's going to drive us to breathe more, okay? So that's kind of our controllers.
Would this be on the exam one, the test one?
Yes, we're going to cut off material for exam 1 whatever we get to today. That's the cutoff point for exam 1, is today.
Okay, because I looked at the study guide and it was I think the next lecture.
As well as on there. Yeah, we're going to cut it off here.
Okay.
We lost a day. And so rather than push the test back another day, we'll just cover that material and put it on the next test. It'll be fine.
Okay. Also, the aerobic testing critique. When are we supposed to be doing that? Because I looked at the schedule and it said that it was gonna be given yesterday. So is it gonna be given today?
Yeah, I think it said on the schedule that it's supposed to be due this Friday.
So what we'll do is, because of the test and everything, is we're going to talk about stuff tomorrow that you're gonna do the critique on. We'll talk about aerobic exercise testing and aerobic prescription tomorrow. And so what I'll do is I'll assign it tomorrow, and then you guys will have until Monday to get it in. We'll just kind of back it up. I don't want you guys to have an assignment to worry about while you're also having to worry about your test, okay? I assume everybody is okay with that, and you're also okay with me chopping the amount of material on the test by 1 lecture. That's not going to be a problem. Because, I guess if we really want to, I can lecture tomorrow and then make tomorrow's info also appear on the test if you'd like for me to. But I don't know. Usually that's not something people want. So, okay. But good questions, Nia. I appreciate you asking.
Can I talk to you after class about class tomorrow? Okay.
Yeah, for sure. Absolutely. Okay. So let me ask it this way. Blake, are you there? I have a simple question for you, Blake. Uh-oh.
Yeah.
You're here. Okay. Blake, if you start exercising, what happens to your breathing?
It gets heavier.
It gets heavier, okay? When does it get heavier?
like while I'm exercising.
Okay. But I mean, if I said, Blake, stand up and start running in place, how long does it take for your breathing to go up?
I don't know, a little bit into it, probably a couple minutes.
A couple of minutes, okay? That would seem like it would make sense, right? It might take a couple of minutes for things, for CO2 to build up in those things. That's actually not what happens. By me merely mentioning to you the thought of you need to go exercise, you have already begun to increase your breathing frequency and your depth ever so slightly. So the next slide shows, so what happens, if these are the things that regulate exercise, what happens when we're going to start doing things is that changes in ventilation occur immediately. You start moving. If I have you guys like raise your arm up over your head, okay? You do something like this, that is enough to evoke an increase in ventilation, okay? And so ventilation goes up in what we call 2 separate phases, okay? And it's these phases that are going to be determined by what the signal is that drives the increase, all right? And so I like to ask that question. Blake's absolutely thinking about this correctly. You would think it might take a couple of minutes because it's going to take a few minutes for me to kind of increase my CO2 levels. Well, CO2 is not the thing that drives the phase 1 or this initial increase in ventilation, okay? So when you start doing things, this initial kind of slope here as we begin in the first few seconds, that is going to occur before there is any change in CO2 levels or hydrogen ion levels or anything. It is mostly driven by changes in body position. It's changed by movement, okay? So have you guys heard of something called proprioception? Anybody, you guys talk about that in physiology at all? Y'all are nodding your heads. Emma, do you remember what proprioception is?
I feel like this is one of those things where it's like I know, but I probably couldn't explain it very well. Like my conception of proprioception is just like your sense of your own body in physical space.
That's 100% correct. It's just a sense of position, right? You put your arm over your head and you know your arm is over your head. Well, how do you know that, right? You're like, well, I don't really know, but it's because of your proprioceptors. And you have these receptors that sense the position of a limb, of a joint. I mean, it tells you where you are in physical space. Are you upside down? Are you right side up? Okay. I can do things like I can vibrate a muscle or a tendon and I can jack up your proprioception. And I can make you think that your arm is in a place where it's not, and all of that. And you lose your sense of position in that way. I can spin you around and make you dizzy, and you can lose your sense of position in space. And so when we activate proprioceptors, or when proprioceptors sense a change in a limb's position, the brain acts as though, ooh, we're about to exercise. We're about to start moving. Something has moved position. We better get ready and start breathing more so that we can bring in more oxygen and make sure we have energy or extra energy to potentially fuel whatever movement is coming, okay? And so that drives this kind of phase 1 or early increase. And then once we get going a little bit, maybe 30 or 40 seconds in, as we begin to use more and more oxygen and produce more carbon dioxide, or as we're doing anaerobic metabolism and we're making lactic acid that dissociates into hydrogen ions and lactate, as CO2 and acidity go up, then that drives this phase 2 that's driven by those chemoreceptors. Okay? And then when you stop exercising, and this is the one that most people kind of have a good sense of, when we stop exercising, your need for oxygen, and because of that, your production of CO2, in a lot of instances, drop off precipitously almost immediately. And yet you continue to breathe more frequently and more deeply for a little while afterwards. And part of what we're doing is we need extra oxygen and things to help us get pH back to normal, to try to get temperature driven back down, to normal levels and to hopefully make sure we're properly regulating carbon dioxide in the blood after all of that. So it stays elevated after exercise, even though we've maybe stopped moving and our immediate metabolic rate has fallen way back down. Breathing's going to stay up. And most people have, that's kind of what most people think of. Well, I exercise and then I stopped and I'm like, I'm really kind of having to breathe hard and I'm sucking it that way. Okay. There are a few breathing irregularities that I want you all to pay attention to. The most common one that we see is something called dyspnea, and this is just shortness of breath. And oftentimes you become short of breath because your respiratory muscles, especially your diaphragm, are poorly conditioned, and you have a hard time either with your respiratory centers or from the sensitivity of your chemoreceptors. You have a hard time adjusting to changes in PCO2 levels. And so CO2 levels are going to go up, but you're not going to be able to increase your breathing sufficiently to do all of that. And so what happens is you're trying to breathe really fast and your diaphragm can't keep up, in essence. And so then you have a hard time actually ventilating and getting air in. You feel like you're short of breath. Okay. Emma, you have a question?
Yeah, so would it also be referred to as dyspnea for people who have shortness of breath because of like pulmonary conditions like COPD, or does it get a different name if it's caused by something that's not like?
No, it's still dyspnea. As far as I'm not a pulmonologist, so I can't say for certain, but no, it's just dyspnea. That we're describing sort of the outcome from all of this. Now the root cause may in fact be different, okay? But the outcome is dyspnea. That is shortness of breath, okay? Another one would be something called hyperventilation, where you're overbreathing rather than not being able to keep up with kind of the driving stuff from your respiratory centers. You're actually forcibly breathing too much. When we do this voluntarily, you can actually reduce your CO2 levels in your blood. So people that are going to do, they do free diving, you got to hold your breath for a long time and you're going to free dive. Then what they will do is they will purposefully hyperventilate before they hold their breath to lower their blood CO2 levels as much as possible. So it's got as much range to go up before they absolutely have to breathe. That can be an issue. Oftentimes when you think of hyperventilation, you think of people that are like freaking out or something and kind of in a stressful situation. Another one that is kind of important, especially during resistance exercise, is something called the Valsalva maneuver. And so the Valsalva maneuver is where you contract your core muscles and your diaphragm and you trap air in the kind of chest cavity or in your lung cavity, and you really ramp up the pressure in there. And so what that does then is it provides support in that cavity, very high intra-abdominal pressures, intrathoracic pressures. And if you're going to lift a heavy weight or you're going to do something like that, then it gives you something to kind of push against, and it prevents internal organs from getting squished, basically. Okay. And so sometimes we do a lot of Valsalva maneuver when you do isometric contractions, like you're pushing against something, you're kind of holding your breath, you're going in that way. Okay. One of the things that happens maybe if you strain when you're having a bowel movement. The problem with the Valsalva maneuver is that because it raises intra-abdominal pressure, it also gives you a very temporary increase in systolic and diastolic blood pressure. And so doing Valsalva maneuvers a lot during exercise or other things can be very dangerous in certain people that are hypertensive. You already have high blood pressure and those kinds of things, and you do a Valsalva maneuver, then you may raise their blood pressure so high that it can be very dangerous. And if you have an aneurysm somewhere or a weak spot in a blood vessel and your pressure goes way up, then that may then lead to a stroke, or it may lead to throwing up a blood clot or something else. And so there's some issues around that. So when you guys see things about prescribing exercise in older adults or in people that are hypertensive, it will talk a lot about making sure that they're not doing Valsalva maneuvers in the same way that maybe younger people are doing. Okay. So the last bit of things that we've got here. Oh wait, Emma, you raised your hand again? No.
Yeah, sorry. I was just gonna ask, you said like doing Valsalva maneuvers like in the same way as other people. So are there modified versions for people who are hypertensive, or is it just like doing less of them?
One, you want to do less, but you really want to have people try to focus on sort of not holding their breath when they're doing a particular lift. Like it's like breathe in, breathe out, breathe in, breathe out in some ways, almost like you're, if you're doing yoga or something, rather than, but you have to really try to focus. It's hard to think about. You have to really think about doing two things at once. Like I'm gonna freaking squat and I'm not gonna hold my breath. Well, I've got, for me, like 150 pounds, but like a regular person, like 400 pounds on their back or something, right? And you're gonna do those things. So it's not really a modified Valsalva. It's just don't Valsalva. Let me be more precise with my language and all of that. Okay. Okay. Cool. So I'm gonna go pretty quickly here through these last bits of things because I think we've covered this already. But what I've got is in the next collection of slides is some graphs showing the responses of certain cardiovascular parameters during exercise. Okay. And so the big take home is they all, for the most part, go up outside of blood flow going to kidneys and the spleen and your liver and kind of your internal organs. Okay. When you exercise, cardiac output is going to increase. We're going to send more blood. Heart rate goes up, stroke volume goes up. Blood flow to your skin goes up. Okay. Blood flow to your brain may increase a little bit, or it may stay the same. Blood flow through your coronary arteries, so blood going to the heart, is going to go up. Okay. So here is a very classic exercise physiology graph. And on the y-axis here, we have cardiac output in liters per minute. And on the x-axis, we have running speed on a treadmill. And this is, this is done using sort of research-related units. So this is the metric system. So it's kilometers per hour. And so you have basically walking right down here. And we've got kind of an all-out sprint all the way on this other end. And what you will note is that there's an almost linear increase in cardiac output as the speed at which we are running on the treadmill is going to go up. So if I'm going to run faster and faster, as I run faster, my muscles have to contract more forcefully. As they contract more forcefully, then I'm forming more cross bridges. As I form more cross bridges, I need to use more energy to break those cross bridges. And so in response to that, cardiac output is going to go up so that we can send more oxygen to those working skeletal muscles so that they can then continue to have enough oxygen to make a sufficient amount of energy to hopefully generate the force required to run at that particular speed. So this is one of the most certain things that we see is that cardiac output is linear related to what we would call exercise intensity. So the faster you run, the more power output on the bike that you've got, or the faster that you're walking, or if you're walking up a hill or something, as intensity increases, therefore metabolic rate increases, cardiac output is going to go up as well. Okay? So as we mentioned the other day, I think it was yesterday, if at rest your cardiac output is maybe 4 or 5 liters per minute, an average person is probably going to be able to increase theirs to maybe 20 liters per minute. So it's up 4 or 5 times. And then in very, very elite athletes, they can get all the way up to like 35 liters per minute. Okay. So the question now is why? What is changing that's making our cardiac output go up? The first of those things is going to be heart rate. Okay. We talked about last week that we can use heart rate as a surrogate for exercise intensity. Heart rate is a surrogate for energy expenditure. And one of the reasons for that is the change in heart rate that drives the change in cardiac output. So heart rate goes up in a linear manner. If I show you a graph of heart rate changes with exercise, it's basically a straight line that looks just like the increase in cardiac output. We make heart rate go up firstly by removing parasympathetic input from the vagus nerve, and then we're going to make it go up even further by increasing sympathetic input, so epinephrine and norepinephrine to the SA node and the AV node into directly onto cardiac muscle. The other thing that changes is that stroke volume also increases, okay? But I want to point this out. Stroke volume goes up until you get to kind of a brisk jog level of exercise intensity, and then stroke volume levels off. Heart rate's going to go up in a linear manner pretty much until you reach age predicted max heart rate, which is going to occur kind of at maximal exercise rates. Stroke volume does not behave that way. Stroke volume goes up, you get to 50–60% of maximal exercise capacity, and then stroke volume levels off the rest of the way, okay? The reason that stroke volume levels off is because the left ventricle is only so big, okay? It's only so big, and because of its size, you can only fit a certain amount of blood into it, and because of the strength of contraction of your cardiac muscle, the heart, the left ventricle can only contract. There's some maximal amount, maximal force that it can exert during contraction. And so when you've maxed out the contractility, okay, and you've maxed out the amount of blood that you can put into it, which is a thing that we call preload, when you max those two things out, then it just can't go up anymore. And we tend to reach that place at about 50–60% of maximal exercise capacity. Okay. One of the things that we're going to see tomorrow is the thing, weirdly enough, that drives changes in cardiac output or increases in cardiac output with exercise training is no change in heart rates, actually changes in stroke volume that are going to be the big drivers of things. We're going to see changes in the left ventricle that are going to make it contract more forcefully, and they're going to make the left ventricle get bigger so that you can put more blood into it, and that's going to drive a lot of our changes that are going to come from those things, okay? If we look at everything, all of you guys are, for the most part, about the same age, right? So how many of you are, let's just say, maybe somewhere between 20 and 23 years old? Like, wave at me if you're between 20 and 23 years old. Almost all of you. If I want to know, all of y'all are about the same age. Almost all of y'all. If I want to know which one of you is going to be the best endurance athlete right now, okay, right now, what I need to know which one of you has the largest stroke volume per your body size, because then that tells me you all have relatively the same age predicted max heart rate, and so you can increase your heart rate all up to the same place. Whichever one of you has the biggest stroke volume in relation to your body size will be able to have the largest cardiac output per your body size, and that's going to mean you are very likely going to have the highest VO2 max. You can use the most oxygen to make energy and then have the best endurance capacity. So, and we'll talk a lot about that tomorrow. Like, what is it that makes stroke volume go up? But stroke volume is the key, okay? As I like to tell people, in this instance, if anybody ever watches Parks and Recreation, and you are a fan of Rob Lowe's character, Chris Traeger, he would always say literally this. But when it comes to endurance exercise, in people that are the same age and roughly the same body size, whoever literally has the biggest heart, literally anatomically has the largest left ventricle, will win the race. And so that's one of the adaptations that we see with exercise, is your heart gets bigger. So you're like the Grinch after Christmas. Your heart grew 2 sizes or something like that. So we'll get into a little bit of that tomorrow. But that's kind of why stroke volume is going to be really, really important. Okay. We're going to talk about how do we get blood back to the heart. So this idea of increasing preload. Preload is the amount of blood that gets into the left ventricle, and we get more of that by having more blood, more venous return coming to the heart. Your veins are pretty cool. The veins have valves in them, and they're real squishy. And so when you contract your muscles, it actually squeezes the veins down. And so you have valves in your veins that prevent the blood from flowing backwards. If you didn't have valves, all the blood in your body would end up in your feet when you stand up all the time. But you do this, you have these valves, and then you contract the muscle, and the muscle squeezes the veins, and it pushes the blood back towards your heart. And so when you exercise, you have more muscle contractions, and it does all of these kinds of things. And it drives blood back to your heart, which actually forces more in more venous returning, which can help lead to an increase in stroke volume, which we don't really have to worry about these kinds of things. Don't worry too much about all of this. The one thing that I do want to hit on all of this, though, is we'll talk about it a little bit more tomorrow, is something called ventricular contractility, and how it's going to help us increase stroke volume, and a thing called the Frank-Starling mechanism. Do you guys talk about this Frank-Starling mechanism or the Frank-Starling law of the heart in like physiology class? You guys heard of that? No, Julia, you're nodding your head. Where have you heard of Frank-Starling?
Personal training class.
So what does Frank-Starling tell us should happen?
So the more your left ventricle gets stretched out, the harder and the stronger it's going to contract to push out blood
Exactly.
for your body.
Very good. You're making your personal training teacher very, very happy right now. So you guys remember last week, I don't remember who I asked to jump, but I asked somebody, may have been Wyatt or somebody, asked him to jump, and they did the sink down and then jump up, do the eccentric contraction before we jump, because we got to stretch and store elastic energy. Your heart's a muscle just like everything else. And so when you force more blood into the left ventricle because of increases in venous return, it fills up and it stretches that cardiac muscle a little bit. And as it stretches, it stores elastic energy, so then it contracts and it releases the elastic energy, and you get a more forceful contraction. So we call this the Frank-Starling mechanism, or the Frank-Starling law of the heart, okay? And at some point, though, we max out stretchiness, and we max out the force of contraction, and at some point, we max out how much blood we can get in there, and that's why stroke volume will plateau, whereas heart rate can kind of keep going up until we reach some kind of age-predicted maximum, because the SA node responds really, really well to epinephrine and norepinephrine, okay? Okay, so if we look at this just kind of from a graphical standpoint, here's the increase in heart rate that's very, very linear. One of the other things that I want you all to pay attention to this, though, so we'll talk about this tomorrow, but max heart rate is related to age. I know I've been saying that. I probably should have introduced that earlier. You take 220 and subtract your age from it, and that's your age predicted max heart rate. So most of you guys, if you're somewhere between 18, 19, 20, 21, 22, your age predicted max heart rate is about 200 beats per minute, give or take a couple of beats, okay? I am 43, so my age predicted max heart rate is 177. I make note of this every time I go to Orange Theory, and I have to kind of look at who, especially when I come here in Norman, and the only other people that are there are college students, and it becomes very obvious why they're kicking my ass at things. I can't increase my heart rate nearly as much as you guys can, okay? So in that particular way, I am losing the ability to increase my cardiac output. So if we're about the same body size, if we have about the same max stroke volume, we have about the same fiber types and mitochondria and things in our muscles, you guys will beat me in a race because you can raise your heart rate more than I can. You can have more cardiac output than I can. And so that's a thing we've always got to keep in mind. Now you get my dad, who is now 74 in like 2 days on all of those things, right? And you can imagine then that his is going to be, let me think about that. His is like 146, okay? And so max heart rate falls and falls and falls, and it drops. One of the things that drops max cardiac output with age. And that's one of the reasons that people's VO2 max and their endurance capacity tends to decline some with age. It's just physiologically impossible to do all of this because your SA node becomes less sensitive to epinephrine and norepinephrine as you age. So that's a thing that happens. We talked about heart rate regulation already. We talked about all of this. We talked about the blood pressure responses. We talked about AVO2 difference and those kinds of things. We talked about the ventilation response to exercise. Let me show you guys one final thing here, and then I'll turn everybody loose for the day. You guys have really hung in there with me. We didn't get a chance to do. I promise tomorrow there'll be more discussion, and we'll do a couple of interactive things, and it won't just be me talking at you guys. So what you guys can see here is a graph that has two y-axes. Okay, we've got the same thing we had before. We've got running velocity in kilometers per hour here on the x-axis. So this is exercise intensity. We have oxygen uptake on one y-axis, and we have ventilation on the other axis. And so here's oxygen uptake. So this is, you can argue that oxygen uptake, this is VO2 or energy expenditure. It could also be a graph of cardiac output or a graph of heart rate. They're all going to track with each other very, very closely. Okay? So just what we would expect as velocity and intensity goes up, O2 uptake goes up, heart rate would go up, cardiac output would go up in this nice linear manner. If you look at ventilation, okay, we see something a little bit different. It's not quite as clean of an increase as what we would see with some of our cardiovascular measurements. So we're here and you're jogging and your ventilation has gone up. You know, if at rest, it's down here, ventilation has gone up, and you're going to go for a while and it goes up in a linear manner. And then we get to this inflection point right here. And it continues to go up in a linear manner, but the slope of this line is going to very distinctly change at this inflection point. We call this the ventilatory break point, okay? The ventilatory break point. So pop quiz on everything. Jacob, are you there? Okay, we got no Jacob. Madison.
Yes.
Do you remember from 10 minutes ago, what is the primary driver of increases in ventilation or breathing and in pretty much every circumstance?
Is it carbon dioxide?
You are 100% correct. Okay, so let's do a little bit of critical thinking. Those Julia and Emma who got to hear me rail against how they never ask you guys to do critical thinking when you're in high school and when you're freshmen and sophomores. Let's do a little bit of critical thinking here. If we look at this and we see a scenario whereby I got a nice linear increase as this is going up. So what's happening to CO2 levels on this part right here? Ventilation is going up. So what by necessity must be happening? It doesn't have to be Madison, it can be anybody. What's happening to CO2 levels here? As ventilation increases, what has to happen to CO2 levels? Come on. Somebody, anybody.
It should also be like going up, right? Like that's what
it's
makes the ventilation.
It's that simple, yes. It's going up. The fact that there is a linear slope to this, let's do some math. What does that tell us about the amount of CO2? As this is going up, as velocity goes up, right, then CO2 is going up in some kind of relatively predictable manner, right? That as this goes up, it's going to go up at a slope that's pretty similar to all of this, okay? Increases, increases, increases. I hit a break point and the slope changes, okay? When the slope changes and it becomes more steep, that means we're all of a sudden, we must be getting more CO2 from somewhere because it's driving a faster increase or a bigger increase in breathing. There is not a corresponding break or shift in oxygen consumption. So remember, I use the oxygen that makes the CO2. And so this graph is not great like this. If I had I need to find a better one. But the slope of the O2 uptake graph and the bottom portion of the ventilation graph, those slopes should be relatively similar, okay? As O2 uptake goes up, ventilation goes up because it's O2, we use O2, we make CO2, it drives the increase. Here, the slope changes. So that means that CO2 content in arterial blood is going up at a higher or a faster rate than what I'm using oxygen. So my question is, where are we getting the extra CO2? Why does it break and go faster? Anybody want to guess?
I have two guesses, one of which feels very far out. So I'm going to start with the one that doesn't feel that weird.
Okay.
My first one would just be that, like, as we're like breathing harder, is it like harder to get some of the CO2 out, and so some of the CO2 that we're producing like kind of gets stuck?
That's a very reasonable guess, Emma. That is, as far as I'm aware, that is not correct. I don't think that ever really happens. I mean, I guess if we change the atmospheric partial pressure of CO2 enough, we could make that happen. But there's so little CO2 in atmospheric air that it's really, really easy. You get any of it in your lungs, it's going out, basically, because the PO2 or PCO2 in atmospheric air is just infinitesimal in that way. Maybe on like Venus or someplace where there's lots more CO2, where it's 1,000 degrees because of all the freaking CO2. That would be worse. What's your second guess?
My second guess is that if ventilation is based on chemoreceptors, well, I guess I can't remember, are the chemoreceptors detecting bicarbonate, or are they detecting like the acid that's associated with the bicarbonate?
So they can detect the acid. They can detect the hydrogen ions. Okay. They can't detect the bicarbonate all by itself. But do we remember what happens to bicarbonate when it buffers something, when it gets to the lungs? It reverses that process and it gives off its CO2. So you're close.
So does it have something to do with like the fact that as you're like working your muscles more, they're going to turn to fermentation and it's going to produce like more acid, and so your chemoreceptors are still detecting acid and they're like, more CO2, and they make you breathe faster?
Yes. And all of that bicarbonate in your blood begins to buffer the hydrogen ions from the lactic acid that you're producing via anaerobic metabolism. And then so what you're doing is, here the ventilatory breakpoint is synonymous with something called lactate threshold, okay, which maybe you guys have heard of before. But at some point, you are going to, if you're exercising hard enough, your aerobic metabolism is not going to be sufficient to keep up with and make enough ATP for all of the cross-bridge detachments that you're doing. And so anaerobic metabolism is going to begin to kick in more and more. And at some point, you're going to have so much anaerobic metabolism that we're going to begin to see an increase in lactate in your blood. So you do anaerobic metabolism, you do glycolysis, you make lactic acid at the end, and then that lactic acid dissociates into lactated hydrogen, and we take the lactate and then put it in the Krebs cycle, and you make energy out of it. The hydrogen ions are going to get bound up by bicarbonate, or at least most of them will. And that drives CO2 out of bicarbonate at the lungs so that you breathe it off. So what happens here, this disproportionate increase occurs at a metabolic intensity that is right around what we call lactate threshold. And if you get too much over this ventilatory breakpoint, you're going to get tired. You're going to fatigue. You can't continue exercising for very long if we get over that. So anyway, y'all talk a lot more about that in Exercise Phys. I just like to do this kind of as a thought exercise to get you guys to think. If we understand enough about kind of how breathing is regulated, and I know we've not really talked about metabolism at all, but kind of how metabolism is regulated, and when you see these kinds of changes, then there's a very reasonable kind of prediction that we can make from that. Okay, Nia, you've been waiting patiently. You can ask your question or make your comment, and we'll go back to Emma, and then we'll shut it down for today.
Okay, so as ventilation like increases, carbon dioxide increases as well, and oxygen?
Yes. Okay. Emma, you have another question or another comment?
Yeah, so I just like kind of wanted to confirm. So basically the ventilatory breakpoint corresponds to where like anaerobic metabolism kind of reaches like a critical point where the acid kind of starts like essentially contributing more enough to the blood that the bicarbonate gets stuck in there?
Correct.
Okay.
It's the point at which there's enough anaerobic metabolism that is occurring that we're probably going to begin to see a shift, a decrease in like blood pH and things. And we're going to begin to see the appearance of lactate in the blood because we're making more than we can reasonably kind of shuttle around and handle inside of our skeletal system. And that is a parameter that can be measured that can be predictive of sort of fatigue or eventual fatigue and eventual exercise performance. Okay, very good. I'm going to stop sharing.